Okay, so what we're going to talk about now is we've talked about how the limit of the sequence of partial series is equal to the value of the infinite series. And now we're going to talk about some random stuff and then show you what the formula becomes for geometric series by looking at it that way. So let me go into the writing mode. Okay, boom. Okay, so one of the things I want to talk about before we actually talk about the geometric sequence is that you can what's called re-index things. So let's say you have the sum from n equals 1 to infinity of 1 half to the n minus 1. You can write this in a variety of different ways. Let's say that you wanted to start your... Or let's say you wanted to rewrite this as 1 half n minus 5 for some reason. You see how before it was n minus 1 as the power, now it's n minus 5? Okay, so it's pretty easy how to do this. You would take n equals 1, and you would substitute it into n minus 1, which if you were to write it in Wolfram, you would write n minus 1 slash dot n arrow 1. If you plug n equals 1 into there, what do you get? If you plug n equals 1 into n minus 1, what does n minus 1 become? 0, right? If you plug n equals 1 into here, the first power is 0. So what that means that the same thing needs to happen over here. Whatever you're plugging into n needs to set n minus 5 to 0. So what does n have to be? So when you plug in your starting number, it needs to make n minus 5 0, because when you plugged in n equals 1, n minus 1 was 0. You need n minus 5 to be equal to 0, so n would start at 5. So this is called re-indexing. Oh shit, my camera's off. Fail. So we call this re-indexing. Okay. Usually we like to start at 1, but sometimes you might start on this one at 5. It would be possible to work backwards to figure out where you'd want to start. So let me do another one. Let's say you have the sum of n equals 2 to infinity of 1 over n squared. So you're looking at this and you're like, I don't like this. I start at 2. I would like to start at 1. So you're like, I need to rewrite this with a new variable m that starts at 1. And will sum from 1 to infinity, not from 2 to infinity. So now the question is, well, what needs to go in here for my formula? Okay. So when I plug in my first value of 2, I get 2 squared, right? So now I'm wondering, like, okay, well, what am I going to have to do here to get it? When I plug in m equals 1, I get 2. So first of all, you can notice you can start with your m equals 1, and you can move the 1 over and you get m minus 1. Okay? Or actually, shit. No, I'm doing that backwards. How do I want to say this? M equals 1. Okay, so if I start with 1 and I want it to be equal to 2, what would I have to do to 1 to get 2? So I would say I have 1 plus x equals 2. Right, because I'm starting at m equals 1, I need to add something to it to get what I would get when I start with 2 over here. So I realize that when I solve for x, I get x equals 1. So that means I'm going to have m plus 1 here. Sorry. So I'm going to take my m plus 1 and I'm going to square it. And that's all over 1. Okay, if you take m equals 1 and you plug it into m plus 1, what do you get? 2, which is exactly what I would have got when I took n equals 2 and I plugged it in. Right, my first term is going to be 1 over 2 squared. My first term for this one will also be 1 over 2 squared. Okay, so you sort of have to like reverse engineer what you need to do to your formula so that when you plug in the 1 that you're starting at here, you get what you got over here when you plugged in 2. I'm not sure of like another way to explain that. Does that make sense or no? Okay, cool. I guess let's do another one. They're a little tricky. Yeah, you basically just like, I just sort of mess around with it until I get the numbers that I need. So it's like, you start with n equals 3, you go to infinity, and let's just say you have, I don't know, let's just make some junk up here. N minus 6. So what I do is I would plug that in. I'd be like, okay, I plug in 3, and I get 3 minus 6. What's 3 minus 6? Negative 3. And then I'd come over here and I'd be like, okay, I'm going to have some new variable, let's call it k. My k is going to start at 1. So what do I need to do to k, which starts at 1? I need to add something to it so I get negative 3. If you subtract 1 from both sides, you get minus 4. So according to this, I need k minus 4. Because if you plug in k equals 1, what's 1 minus 4? The negative 3 that I got over here. Just like when I plug n equals 3 into n minus 6, I get negative 3. Okay, so we call this reindexing. It's like a super common thing. Hopefully these examples are making sense. Like I think of it, it's not quite guess and check, but it's like it doesn't look very elegant. That's what I'm gonna say. Okay. So now we can talk about the geometric series. Okay, so I want a formula for the sum of n equals 1 to infinity of the geometric series, which is a times r to the n minus 1. Okay, where a is your starting number and r is your common ratio. The number r is the number you multiply by to get the next term in the sequence. Okay, and we have said that, hey, the infinite series is equal to the limit of the partial series, correct? Which is the limit as k goes to infinity of the sum n equals 1 to k of a times r n minus 1. So what we need to do is we need to find a formula for this sum. We need to find a formula for sk. So we get to work on this. We're like, okay, sk, that's the sum where n goes from 1 to k of a times r n minus 1. And let's just plug in these terms. I'm going to get a times r 1 minus 1 plus a times r 2 minus 1. Forget to put the plus. Dot, dot, dot. What's my last term look like? A r k minus 1. You see I plugged in n equals 1, n equals 2, dot, 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 n equals k. So let's make some simplifications here. 1 minus 1 is 0, right? And what's r to the 0? R to the 0 is just 1, right? So that term goes away and you just get a. Okay, 2 minus 1 is 1, so you get a times r to the first. The next one would be a times r to the second. all the way up to a times r to the k minus 1. That's what sk is equal to. Well, we can, and we're about to do that, yes. So, let's start by factoring out an a. So if you factor out an a, you're going to get 1 plus r squared plus dot 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 r to the k minus 1. And what is this equal to? It's equal to sk. Okay, now you look at this, and you can't really factor that thing on the right. I mean, I wish I could, but there's nothing I can think of. So you come up with a better idea. What you actually do is multiply by something that will allow some canceling to happen. So it's like you're doing the reverse of factoring. You're like, fuck it. Let's just multiply by 1 over r because some nice shit is going to happen, basically. So let's look at what that nice stuff is going to be. So let's forget about this a for a moment. And let's set up our multiplication. You're going to get 1 times 1. Boom. And you're going to get r times 1, which is r. And you're going to get r squared times 1, which is r squared, plus dot 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 plus rk minus 1 times 1, which is just rk minus 1. Agreed? I just multiply everything out by 1, and that's what I get. Now, what am I also going to have to do? I'm going to have to multiply all those terms by 1 minus r. Now notice, because they're all positive, I can just put minus now. And then forget about the fact that there's a minus there. So my first term will be 1 times r, which is r. And then what's my next term going to be? R times r, which is r squared. R squared times r is r cubed, and then plus dot 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 rk minus 1 times r is just rk. Exactly, yes. And that is exactly the whole point here, because you're like, oh shit, the r and the r cancel, the r squared and the r squared cancel. Everything up to rk minus 1 cancels, leaving us just with 1 minus rk. So you get a 1 minus rk. And what is this equal to? 1 minus r sk. And then there you go. You're like, oh shit, my formula for the sum of sk is going to be a times 1 minus rk all over 1 minus r. So like, shit, like, if I know what my geometric sequence is, the sum of the first k terms is going to be whatever you get when you plug in those numbers, where a is the starting number for the sequence, and then r is your common ratio. Now this is the cooler thing. I actually know that the infinite sum is equal to the limit of the partial sums, and I actually have a formula for the partial sums now. So the infinite sequence is equal to the limit as k goes to infinity of a times 1 minus rk all over 1 minus r. Now, this is the cool thing. The only term in here that is affected by the limit is this one right here with the RK, right? If R is less than 1, what happens if you take a number that's less than 1 and raise it to higher and higher powers? Like 1/2 to the 5th, 1/2 to the 10th, 1/2 to the 100th. If you keep on, they go to 0, right? So what that happens is if you take the limit as k goes to infinity, the RK just goes away and you get a times 1, which is just a over 1 minus r. So if your r value is a number between -1 and +1, not including them, you get that. What about if r is equal to 1? So if r is equal to 1, 1 to higher and higher powers just is 1, right? And you get 1 minus 1, which is 0. And if you have, well, I guess more importantly, what happens to the bottom? Yeah, you get a 0 in the denominator, which means that it's undefined. So this doesn't work if r equals 1 in your geometric sequence, because you would get undefined in the denominator, right? If r equals 1, you get 1 minus 1 on the bottom. It basically, what this tells you is that if r equals 1, you're adding up the same number over and over, right? Because you're multiplying each term by 1 each time. That would add up to infinity. Now the other case is if r is bigger than 1. Okay, what happens if r is bigger? If you take a number bigger than 1 and raise it to higher and higher powers, what happens? Yeah. In other words, the limit will diverge. So if r equals 1 or it's bigger than 1, your sequence will diverge. But if r is less than 1, your sequence will converge. And you can add up all those infinite number of terms by using the formula a over 1 minus r. Okay, now you have to be very careful, because this only works when your formula is a times r to the n minus 1. So for instance, let's say you're doing the sum n equals 1 to infinity of 2/3 n plus 2. Okay, remember it's the formula, the form is a r to the n minus 1. So obviously what's your a? Your a would just be 1, right? But it's r to the n minus 1. This is written as r to the n plus 2. So this is why you need a reindex, right? Remember how I talked about that earlier? So if you plug in n equals 1 into n plus 2, what is the first term going to look like? You're going to get r to the 3rd, right? And I'm going to rewrite this as the sum for m equals 1 to infinity of 2/3 to the something. So my m is 1. I want 1 plus something to be equal to 3. So if I subtract 1, I get 2. So what I want is... Oh shit. I guess we should start backwards here. My bad. We don't know what m will start at. I want this to be m minus 1. Okay, what does m minus 1 have to be equal to? 3. So I would need my m to start at 4. Okay. So then what you would have to do is you would do the infinite sum, but the infinite sum starts at 1. And then you'd have to remove off the terms, the extra terms. You see how this infinite sequence, it starts at 4? But if you were to plug into the formula, the infinite sequence would start at 1. You'd have to remove the first term, the second term, and the third term. So you would just like peel those off after you compute it. So what you would do is compute S, and then you'd have to subtract A1, A2, and A3 because they're not included in this one because it starts at the fourth term. That's one way you could do it. Let's do it another way. So another helpful way to do this is actually compute the terms. So you would get 2/3. Okay, if you plug in n equals 1, do you see how you start off on the third? 2/3 to the third power. And then you would get 2/3 to the fourth power, and so on. Okay, so do you see how everything you could factor out a 2/3 squared? And then this one would be 2/3 plus 2/3 squared. So this would be 2/3 to the first, and then you'd have like 2/3 to the third with all of those terms. So what that's showing you is that you could rewrite it as the sum where n equals 1 to infinity of your first term would be what is 2/3 to the third? Let's rewrite that. 2/3 to the third would be 8. What's 3 to the third? Is it 27ths? Thank you. Plus all those other terms. So you'd have as your A, your 8/27ths times 2/3 to the n minus 1. So that's one way you could do it. That's sort of an easier way. Sometimes I like to, it depends on the case. Like usually this one works best, but sometimes the other way is a nicer way to do it, where you re-index it and then just remove off the terms that you don't want. So then we could actually figure out the sum. You just identify what A is. A is 8/27ths. R is 2/3. We know that the infinite sum is A over 1 minus R. Our A is 8/27ths. We get 1 minus 2/3. So you get 8/27ths divided by, what's 1 minus 2/3? 1/3? Yeah. And then you get 8/27ths times the reciprocal of 1/3, which is 3 over 1, and then you get some canceling. The 3 and the 27 will leave you with 9 on the bottom, so you get 8/9. So if you add up all those terms in the sequence, what do you get? Just 8/9. Hopefully this looks familiar from pre-calc. Do you remember doing this in pre-calc? Like infinite geometric series and stuff like that with this formula? Hopefully you've seen it before. Oof, that was a lot. Okay, I think we're just going to take another break.